there is a technical paper which is available with the presentation, and will highlight DIWA experience, advantages and disadvantages, and lesson learned for power augmentation of 322 megawatt utilizing ambient-dependent technology such as evaporative cooling and fogging, and non-ambient dependent technologies which is wet compression and GT inlet air chilling. DIWA starts with efficiency from the design stage. DIWA is producing power and water together, and we look at efficiency and optimization at the design stage. So we look at the best or the optimum power plant design, and this looks at the capital cost and operation cost together. And something else also was developed in DIWA, which is called second stage optimization. We look at this power plant. Many times you will find that the power plant, based on the power to water ratio, you will come up with a power plant which is optimum, meaning that unit cost total or the fuel burn for producing the power and water requirement is minimum. And this is what everybody wants to achieve that, which includes the total cost. Then we go into, in this design, normally, depending on the power to water ratio, you will find that cogeneration plant, which is gas turbine with utilizing the waste heat from the gas turbine. And sometimes you have supplementary firing, and then you have the back pressure steam turbine with running desalination plant. Normally, this design gives you the highest utilization factor of energy, which is driven really by the power to water ratio requirement for your design. And sometimes, depending on the requirement, still you end up with condensing turbines with extraction to desalination plant. Now, we are fully aware that this might not be the optimum, because sometimes the optimum design could be hybrid design. Hybrid means that you will end up with RO and MSF, 20, 80, okay, through techniques of optimization. But we choose not to go with RO. Most, as a thumb rule, when you have power to water ratio in the range between 12 to 14, you will end up, the optimum power plant design will be cogeneration, back pressure steam turbine, and desalination plant. We went into a different approach. We looked at, okay, these plants were run and will be maintained during the life cycle of the plant, and how they will fit. This is the second stage. How they will be operated and fit within the fleet and will be committed. And something we found, and that the auxiliary boilers, normally for optimum power plants, you will find that the boilers are low pressure boilers and installed at the low pressure. That gives you the minimum cost for the plant. And when we studied the design, we found, no, we will put it on the high pressure side, it costs more. But we find that it improves the efficiency of operation depending on the outages, and this was really implemented in one of the plant L phase 1. And return, we thought it would take 3 years, actually it took few months. So this is to emphasize that DIWA really put huge effort in the first step, which is optimum power plant design. The optimization technique was really introduced in DIWA for cogeneration system and the unit commitment. So it was here developed and then taken somewhere. So this part, and then we link also in the optimization is the outage planning, which is very critical. Now, if you want to optimize, you cannot separate these two processes. They have to work together. And then DEWA has done repowering projects to improve efficiency, reduce emission, and then went into power augmentation. Now, here is the DEWA heat utilization. And if you can see, the base station or energy utilization is in the range of, we are reaching almost 90% in the biggest plants that we have. And our capacity with M station is around 9,640 and water 470 MIGD. So most of our new stations, you are talking about energy utilization above 80%, reaching to 90%. When we benchmark, this is actual with normalized efficiency with the year 2000. What we achieved is 20.45%, or say 20.5% improvement in efficiency. Now, in the technical paper, you will find that this same graph showing 118.5, because when I did the technical paper, at that time I didn't have the actual of 2010. So actually, there was a projection. The actual performance in 2010 is much, much better. And this 20.45%, if business was as usual and we expanded, we will be spending 20% of fuel. It's a huge amount. Now this one corresponds, just for the 2010, to 3.8 million tons of CO2 saved. Now most of the power plants that we have are cogeneration, gas turbine, driven with utilizing the waste heat. And this is really a good design. Let me put it this way. We're talking here, the speaker before me was talking about energy and efficiency, and it's very important to us. Actual figures, 2010 I don't have, but 2009, 62% of our water production is produced by waste heat. That means no fuel was burned. And around 15% of our electricity was produced by waste heat. That's 2009 figures. I expect the 2010 to be much better. Now, the gas turbine principle is very simple. So we need the power plants and the highest production, the peak in the summer. But in the summer, our gas turbine output reduces because air density is the problem. Now, air in the summer is less dense, compressors less efficient, a volume of air for combustion is less, output is less. Normally, for each 1 degree temperature, for the F class, the big units around 1.8 megawatt reduction, for the E class around 0.9 for each degree ambient increase. So if you see here, around, in this region, around 20% of capacity that we paid for, we cannot utilize. This is the output, the gas turbine. So now technology, which is proven technologies, and some of the technology actually was joint ventures between DEWA and